Thank you for being here. As you settle in and prepare for a restful night, let your imagination drift to the far reaches of our galaxy. Beyond our solar system lies a vast and mysterious universe filled with countless wonders, including the fascinating worlds known as exoplanets. These distant planets, orbiting stars far from our own, offer a glimpse into the incredible diversity and complexity of the cosmos. From planets with two suns to those where it rains molten glass, the realm of exoplanets is filled with astonishing discoveries that can spark our curiosity and inspire dreams of the unknown. So, as you relax and let your mind wander, here are surprising facts about exoplanets to help you drift off into a serene and starry slumber. 1. The first confirmed exoplanet discovery was made in 1992 by astronomers Alexander Volsch-Chan and Dale Frail. They discovered the planets orbiting the pulsar PSRB1-57+12, marking a groundbreaking moment in astronomy. These planets were intriguing because they orbited a pulsar, a type of neutron star left over from a supernova explosion, which was previously thought to be an unlikely environment for planet formation. This discovery challenged existing theories and opened up new possibilities for where planets might be found. 2. There are over 5,000 confirmed exoplanets in our galaxy, with thousands more candidates waiting to be confirmed. This staggering number reveals the vastness and richness of planetary systems in the Milky Way. These exoplanets exhibit a tremendous variety in size, composition, and orbital characteristics, demonstrating that planetary formation is a common and diverse process across the galaxy. 3. Exoplanets can be significantly larger than Jupiter, the largest planet in our solar system, or smaller than Earth. Some exoplanets, known as super-Earths, have masses up to 10 times that of our planet and may have both rocky surfaces and thick atmospheres. Conversely, some exoplanets, called mini-Neptunes, are smaller versions of the gas giants in our solar system, featuring deep atmospheres of hydrogen and helium. For some exoplanets have incredibly short orbital periods, completing a full orbit around their star in just a few days. These planets, often referred to as hot Jupiters, are gas giants that orbit extremely close to their stars, resulting in very high surface temperatures. On the other end of the spectrum, there are exoplanets with orbits that take hundreds or even thousands of Earth years to complete, such as the distant gas giants orbiting at the fringes of their star systems. 5. The term exoplanet is short for extrasolar planet, meaning any planet that exists outside of our solar system. These planets can be found in a variety of star systems, including those with single stars, binary stars, and even multiple star systems. The discovery of exoplanets in such diverse environments has expanded our understanding of the potential for planet formation and the conditions that might support life. 6. The closest known exoplanet to Earth is Proxima Centauri b, which is just 4.24 light-years away. This rocky planet orbits Proxima Centauri, the closest star to our solar system. Proxima Centauri b is located within its star's habitable zone, where conditions might be right for liquid water to exist on its surface. This proximity makes Proxima Centauri b a prime candidate for future missions aimed at searching for signs of life beyond our solar system. 7. Some exoplanets orbit to stars, much like the fictional planet Tatooine from Star Wars. These planets, known as circumbinary planets, experience a unique gravitational environment due to the influence of two suns. The discovery of such planets has shown that planetary systems can be more complex and varied than previously imagined, and they challenge our understanding of planet formation in multi-star systems. 8. There are rogue exoplanets that do not orbit any star and instead wander freely through the galaxy. These free-floating planets are thought to have been ejected from their original star systems due to gravitational interactions or stellar events. Studying rogue planets can provide insights into the dynamics of planetary systems and the processes that can lead to planet ejection. 9. Hot Jupiters are a class of exoplanets that are similar in size and composition to Jupiter but orbit very close to their stars, resulting in extremely high surface temperatures. These planets often have orbital periods of just a few days and can exhibit dramatic atmospheric phenomena such as strong winds and intense heat. The existence of hot Jupiters was unexpected and has led to new theories about planetary migration and the dynamic evolution of planetary systems. 10. Some exoplanets have extreme and exotic atmospheres. For example, the planet HD 189733b experiences glass rain, where silicate particles condense in the atmosphere and fall as glass shards driven by fierce winds. Other exoplanets have atmospheres filled with vaporized metals, clouds of sulfuric acid, or thick layers of methane and ammonia. These diverse atmospheric compositions illustrate the wide range of environments that can exist on planets beyond our solar system. 11. Exoplanets known as water worlds are hypothesized to be composed mostly of water, potentially with global oceans hundreds of kilometers deep. An example is GJ1-14b, which orbits a red dwarf star about 40 light-years away. These planets could harbor life in their deep oceans, shielded from the harsh conditions of space by thick ice layers or atmospheres. 12. The concept of a habitable zone, also known as the Goldilocks zone, refers to the region around a star where conditions might be just right for liquid water to exist on a planet's surface. This zone varies depending on the star's size and temperature. Finding exoplanets within these habitable zones is a key focus in the search for potential life beyond Earth. 13. Some exoplanets experience extreme axial tilt, which can result in dramatic seasonal variations. For example, the planet Uranus in our solar system has an axial tilt of about 98 degrees, causing extreme seasonal changes. Exoplanets with similar tilts may have complex climate patterns that influence their habitability. 14. Exoplanets can have rings like Saturn, but these rings can be much larger and more massive. The planet J1407b, for instance, is believed to have a ring system about 200 times the size of Saturn's rings. These massive rings could affect the planet's temperature and the dynamics of any moons orbiting within them. 15. Some exoplanets have highly eccentric orbits, meaning their distance from their star varies greatly over the course of their orbit. This can lead to extreme changes in temperature and climate. An example is the exoplanet HD 20780b, which has the most eccentric orbit of any known planet, swinging from a close approach to its star to a far distant one. 16. Exoplanets can be tidally locked to their stars, meaning one side always faces the star while the other side is in perpetual darkness. This can create a stark contrast in conditions between the day side and the night side. An example is the planet Proxima Centauri IB, which might be tidally locked to its star, leading to extreme temperature differences. 17. The search for exoplanets has led to the discovery of planets in unexpected places, such as within the remnants of dead stars. One such planet, PSRB 16-026b, orbits a pulsar and a white dwarf in a binary star system. This zombie planet challenges our understanding of planet formation and survival in such harsh environments. 18. Exoplanets can have wildly diverse weather patterns. For example, the gas giant HD 189733b experiences violent winds of up to 5,400 miles per hour, 8,700 kilometers per hour, and temperatures around 1,700 degrees Fahrenheit 930 degrees Celsius. Understanding these extreme weather systems can help us learn more about atmospheric dynamics on other planets. 19. Some exoplanets may have surface conditions similar to Earth, with oceans, continents, and possibly even a climate conducive to life. One such candidate is Kepler 5b, which orbits within the habitable zone of a Sun-like star. It is sometimes referred to as Earth's cousin due to its similar size and orbit. 20. The study of exoplanets is not only about finding life, but also understanding the diversity of planetary systems. The variety of exoplanets discovered so far, from gas giants to rocky worlds, from hot Jupiters to icy bodies, helps scientists refine their models of planet formation and evolution, offering insights into the past and future of our own solar system. 21. Exoplanets known as super-Earths are a class of planets with masses larger than Earth but smaller than those of ice giants like Uranus and Neptune. These planets can be rocky like Earth or have thick gaseous atmospheres. Their diverse characteristics make them intriguing targets in the search for potentially habitable worlds. 22. Some exoplanets have unusually low densities, often referred to as puffy planets. These planets, such as HATP-1b, are much larger in diameter than expected for their mass, suggesting that they have extremely thick, low-density atmospheres. Studying these planets can provide insights into atmospheric processes and the effects of intense radiation from their stars. 23. The Kepler Space Telescope, launched by NASA in 2009, revolutionized the search for exoplanets by using the transit method. This method detects the slight dimming of a star as a planet passes in front of it. Kepler's mission led to the discovery of thousands of exoplanets and transformed our understanding of the prevalence of planetary systems in our galaxy. 24. Exoplanets can have unique and exotic climates. For example, the planet Kepler-10b, a rocky exoplanet, is so close to its star that its surface temperature is estimated to be over 3,000 degrees Fahrenheit, 1,650 degrees Celsius. This extreme heat likely causes the surface to be molten with a landscape of flowing lava. 25. The discovery of exoplanets around Sun-like stars suggests that planetary systems like our own might be common in the galaxy. For instance, the TRAPPIST-1 system has 7 Earth-sized planets orbiting a red dwarf star, with 3 of them located in the star's habitable zone. This finding raises exciting possibilities for the presence of life. 26. Some exoplanets, known as Chthonian planets, are believed to be the remnants of gas giants that have had their atmospheres stripped away by their star, leaving behind a dense, rocky core. These planets provide a glimpse into the processes of planetary erosion and the fate of planets in harsh stellar environments. 27. The atmospheres of exoplanets can be studied through a technique called transmission spectroscopy. When a planet transits its star, some of the star light passes through the planet's atmosphere, allowing scientists to detect the presence of specific gases such as water vapor, carbon dioxide, and methane. This method helps identify potential signs of habitability and even biosignatures. 28. Exoplanets can exhibit fascinating orbital resonances where multiple planets exert gravitational influences on each other, leading to stable orbits with specific ratios. For example, the planets in the TRAPPIST-1 system are in a complex resonance, which helps maintain the stability of their orbits despite their close proximity to one another. 29. Some exoplanets are located in binary star systems where the stars orbit each other. These planets can have complex and dynamic environments due to the gravitational effects of both stars. An example is the planet Kepler-16b, which orbits the stars and experiences variations in its climate due to the changing positions of its suns. 30. Exoplanet research is advancing rapidly with the development of new telescopes and technologies. The James Webb Space Telescope JWST, launched in 2021, is equipped with advanced instruments capable of studying the atmospheres of exoplanets in unprecedented detail. JWST's observations are expected to revolutionize our understanding of the potential for life beyond our solar system. 31. Some exoplanets have orbits that are highly inclined relative to the equatorial plane of their stars. These misaligned orbits can result from gravitational interactions with other planets or stars in the system. Studying these misaligned orbits helps astronomers understand the dynamic processes that shape planetary systems. 32. Exoplanets can also have moons, known as exomoons. While no exomoon has been definitively confirmed yet, their presence is suggested by the complex gravitational interactions observed in some planetary systems. Exomoons could potentially harbor life, especially if they orbit planets within the habitable zone 33. The Test Transiting Exoplanet Survey satellite mission, launched by NASA in 2018, aims to discover exoplanets around the brightest stars near Earth. TESS uses the transit method to identify exoplanets and is expected to find thousands of new exoplanets, including many Earth-sized and super-Earth planets 34. Exoplanets can vary significantly in their potential for habitability. For instance, planets orbiting red dwarf stars might be subject to intense stellar flares and radiation, which could strip away atmospheres and affect the potential for life. Understanding these environmental factors is crucial for assessing the habitability of exoplanets 35. Some exoplanets are located in systems with multiple planets that exhibit a wide range of sizes and compositions. These diverse planetary systems provide valuable data for studying how planets form and evolve. For example, the Kepler-90 system has 8 planets, making it one of the most complex systems discovered so far, 36. The method of direct imaging allows astronomers to take pictures of exoplanets by blocking out the light from their parent stars. This challenging technique has successfully captured images of a few exoplanets, such as the planets orbiting the star HR 8799. Direct imaging provides direct information about the exoplanet's atmosphere and surface, 37. Some exoplanets have been found to have extremely long orbital periods, taking hundreds of Earth years to complete a single orbit around their star. These distant planets, such as the gas giant HIP 11915b, challenge our understanding of how planetary systems form and remain stable over long time scales, 38. The study of exoplanets has led to the discovery of planets with unusual and extreme weather patterns. For example, the planet WASP-76b experiences temperatures so high that it rains molten iron. Such extreme conditions provide insights into atmospheric dynamics and the potential for diverse climates in the universe, 39. Some exoplanets, known as subneptunes, are smaller than Neptune but larger than Earth. These planets often have thick atmospheres of hydrogen and helium and may possess water or ice layers beneath their atmospheres. Subneptunes are among the most common types of exoplanets discovered, indicating a significant variety in planet formation processes. 40. The detection of exoplanets has revealed that planetary systems can have highly diverse architectures. For instance, some systems have closely packed planets with short orbital periods, while others have wide separations between planets. Understanding these different system architectures helps scientists learn about the processes that lead to the formation of planets and their orbits. 41. Some exoplanets have been found to have super-Earth characteristics, meaning they are larger and more massive than Earth, but smaller than Neptune. These planets, such as 55 Cancri, often have extremely high surface temperatures and may possess unique geological features due to their size and composition. 42. The study of exoplanet atmospheres has uncovered a wide range of chemical compositions. For example, the atmosphere of the exoplanet WASP-39b contains water vapor, sodium, and potassium. By analyzing these atmospheric compositions, scientists can infer details about the planet's formation history and potential for supporting life. 43. Some exoplanets are located in star systems with multiple stars, creating complex gravitational environments. For instance, the planet HD 188,753 orbits a star that is part of a triple star system. These multi-star systems provide unique laboratories for studying the dynamics of planetary orbits and the influence of multiple gravitational forces. 44. The study of exoplanet transits can also reveal the presence of rings or large moons. When a planet with rings transits its star, the rings can cause distinctive dips in the star's light curve. Detecting these features helps scientists understand the formation and evolution of planetary rings and moons. 45. Some exoplanets exhibit unusual densities, suggesting they may be composed of exotic materials. For example, the planet Kepler-10c is much denser than expected for its size, indicating it may have a composition rich in heavy elements like iron and rock. These discoveries challenge existing models of planet formation and composition. 46. The discovery of exoplanets has also provided insights into the potential for life in extreme environments. For instance, some exoplanets orbit stars that emit intense ultraviolet or X-ray radiation, which could sterilize their surfaces. Studying these harsh conditions helps scientists understand the limits of habitability and the resilience of life. 47. Some exoplanets, known as carbon planets, are theorized to have compositions rich in carbon rather than oxygen. These planets could have surfaces covered in graphite or diamond, creating entirely different geological environments from those found on Earth. The existence of carbon planets expands our understanding of the diversity of planetary types in the universe. 48. The search for exoplanets has revealed that planets can form around a wide variety of star types, including very low-mass stars and brown dwarfs. These discoveries suggest that planet formation is a common and robust process that can occur in diverse stellar environments. 49. The study of exoplanets has led to the development of new methods for detecting and characterizing planets. Techniques such as gravitational microlensing, which detects planets by observing the bending of light from a distant star, have provided additional tools for discovering planets in a wide range of environments. 50. Exoplanet discoveries have inspired a renewed interest in the search for extraterrestrial life. Missions like the Search for Extraterrestrial Intelligence (SETI) use radio telescopes to listen for signals from advanced civilizations on distant planets. The discovery of potentially habitable exoplanets has increased the hope of finding signs of life beyond our solar system. 51. The study of exoplanets has revealed that planets can form in very diverse environments, including the dense regions near the centers of galaxies. These regions, often populated by older stars and rich in heavy elements, could host unique planetary systems. Understanding these environments helps scientists learn more about planet formation under different conditions. 52. Some exoplanets have been discovered around white dwarfs, the remnants of stars that have exhausted their nuclear fuel. For example, the planet WD-1856b orbits a white dwarf and has a very short orbital period. Studying these planets can provide insights into the fate of planetary systems as stars evolve and die. 53. The discovery of exoplanets has challenged our understanding of where planets can exist. For instance, the planet Kepler-1647b orbits to stars and is located in the habitable zone of its system. This circumbinary planet demonstrates that habitable conditions can exist in systems previously thought to be too complex for stable planet formation. 54. Some exoplanets have been found with unusually high metallicities, indicating a composition rich in heavy elements. These metal-rich planets, such as Kepler-10c, may have formed in environments with high concentrations of metals, providing clues about the materials available in their birthplaces and the processes that led to their formation. 55. Exoplanet research has shown that planetary atmospheres can be very dynamic, with features like high-altitude clouds and strong wind patterns. For example, the exoplanet HD 189733b has been observed with blue skies and dynamic weather, including possible silicate clouds. Studying these atmospheres helps scientists understand the diversity of climatic conditions on other worlds. 56. Some exoplanets exhibit significant seasonal variations due to their orbits and axial tilts. For example, the planet Kepler-421b has an orbital period of nearly 700 days, leading to long and intense seasons. These variations can affect the planet's climate and potential habitability. 57. The detection of exoplanets has revealed that planetary systems can have very different architectures from our solar system. Some systems, like the TRAPPIST-1 system, have multiple Earth-sized planets in close orbits, while others, like the HR 8799 system, have widely spaced giant planets. These diverse architectures challenge our understanding of how planetary systems form and evolve. 58. The atmospheres of some exoplanets contain exotic chemicals and compounds. For instance, the atmosphere of the exoplanet WASP-1-1b contains vanadium oxide, a compound that is rare on Earth but common in the atmospheres of hot Jupiters. These chemical signatures help scientists understand the processes occurring in exoplanetary atmospheres. 59. Exoplanet research has revealed that planets can have very different surface conditions from those on Earth. For example, the planet Kepler 5b, located in the habitable zone of a Sun-like star, might have a surface covered in lava due to its close proximity to its star. Understanding these conditions helps scientists explore the range of environments where planets can exist. 60. Some exoplanets are believed to have formed far from their current locations and migrated inward over time. This process, known as planetary migration, can result in planets with unusual orbits and compositions. For example, hot Jupiters are thought to have formed beyond the frost line of their star systems and migrated inward, challenging traditional models of planet formation. 61. The discovery of exoplanets has revealed that planetary systems can be very diverse in terms of the number and types of planets they contain. Some systems have only one or two planets, while others have multiple planets with a wide range of sizes and compositions. This diversity helps scientists understand the variety of ways in which planetary systems can form and evolve. 62. The study of exoplanets has shown that some planets can have very low albedos, meaning they reflect very little light. For example, the exoplanet TRES-TB is one of the darkest known exoplanets, reflecting less than 1% of the light that hits it. These low albedos can provide insights into the composition and structure of the planet's atmosphere. 63. Some exoplanets have been discovered in star systems that are much older than our solar system. These ancient planetary systems can provide valuable information about the long-term stability of planets and the conditions that existed in the early universe. Studying these systems helps scientists understand how planets and their environments change over billions of years. 64. The study of exoplanets has revealed that planetary systems can have very different compositions from our own. For example, the Kepler 36 system has two planets with very different densities and compositions orbiting very close to each other. This diversity challenges our understanding of planet formation and the factors that determine a planet's composition. 65. Some exoplanets have been found with very high eccentricities, meaning their orbits are highly elliptical rather than circular. These eccentric orbits can result in extreme variations in temperature and climate as the planet moves closer to and farther from its star. Understanding these orbits helps scientists learn more about the dynamic processes that shape planetary systems. 66. The detection of exoplanets has revealed that some planets can have very long orbital periods, taking hundreds or even thousands of Earth years to complete a single orbit. For example, the planet MASSJ-1268140 has an orbital period of about 900,000 years, making it one of the longest known. Studying these distant planets helps scientists understand the dynamics of planetary systems over long time scales. 67. The study of exoplanets has shown that some planets can have very high surface temperatures, even hotter than some stars. For example, the exoplanet KELT-9b has a surface temperature of about 7,800 degrees Fahrenheit for 1,300 degrees Celsius, making it one of the hottest known planets. These extreme temperatures provide insights into the effects of intense stellar radiation on planetary atmospheres and surfaces. 68. Some exoplanets have been found with very high masses, much larger than any planet in our solar system. For example, the planet Dennis B J08 to 3031 for 91 to 01b has a mass about 28 times that of Jupiter, making it one of the most massive known exoplanets. Understanding these massive planets helps scientists learn more about the range of planet sizes and the processes that lead to their formation. 69. The study of exoplanets has revealed that some planets can have very short orbital periods, completing a single orbit in just a few hours. For example, the planet Kepler-4c has an orbital period of just 7.8 hours, making it one of the shortest known. These short periods provide insights into the dynamics of tightly packed planetary systems and the effects of strong gravitational forces. 70. The detection of exoplanets has shown that some planets can have very high densities, much higher than that of Earth. For example, the planet Kepler-10b has a density of about 8.8 grams per cubic centimeter, making it one of the densest known exoplanets. These high densities can provide clues about the planet's composition and the processes that lead to the formation of dense planets. 71. Exoplanet discoveries have shown that some planets can exist in regions of space previously thought to be unlikely for planet formation, such as the dense environments near the centers of globular clusters. These tightly packed groups of stars provide challenging environments for planet formation due to intense gravitational interactions, but the presence of planets in such regions suggests that planet formation is more resilient than previously thought. 72. Some exoplanets have been discovered in systems where the host star is very young, providing insights into the early stages of planet formation. For example, the planet V830 Tauri b orbits a star that is only a few million years old, offering a glimpse into the processes that occur during the earliest phases of planetary system development. 73. Exoplanets known as superpuffs are characterized by their very low densities, making them appear puffed up for their mass. These planets, such as Kepler-51b, have densities similar to cotton candy, indicating they have thick, extended atmospheres. Studying superpuffs can provide insights into the structure and evolution of planetary atmospheres. 74. The study of exoplanets has revealed that some planets can have significant volcanic activity, similar to Jupiter's moon Io. For example, the planet 55 Cancri is believed to have widespread volcanic activity, with lava flows on its surface. Understanding volcanic activity on exoplanets can provide clues about their geologic and atmospheric processes. 75. Some exoplanets have been found with compositions rich in heavy elements, suggesting they formed in metal-rich environments. For example, the planet TOI8 for 9b has a density indicating a composition primarily of heavy elements, which challenges existing models of planet formation and migration. 76. The detection of exoplanets has shown that some planets can have very high albedos, meaning they reflect a significant amount of light. For instance, the planet Kepler-7b has a high albedo due to the presence of reflective clouds in its atmosphere. High albedos can influence a planet's temperature and climate.
77. Some exoplanets have been found in systems with very high multiplicity, meaning they have a large number of planets orbiting the same star. The Kepler-11 system, for example, has 6 planets in close orbits around their star. High multiplicity systems provide valuable data for studying the dynamics and stability of planetary systems. 78. The study of exoplanets has revealed that some planets can have unusual shapes due to their rapid rotation or strong tidal forces. For example, the planet WASP-1b is elongated due to the gravitational pull from its host star, creating an egg-like shape. Understanding these deformations can provide insights into the physical properties and internal structure of exoplanets. 79. Some exoplanets are found in systems with very old stars, providing clues about the longevity and stability of planetary systems. For instance, the planet PSRB 1620-26b orbits a pulsar and a white dwarf that are part of an ancient star cluster. Studying these ancient systems helps scientists understand the long-term evolution of planets and their environments. 80. The study of exoplanets has shown that some planets can have significant magnetic fields, which can influence their atmospheres and potential habitability. For example, the planet HD 209458b shows evidence of a magnetic field that interacts with its star's solar wind. Understanding magnetic fields on exoplanets can provide insights into their internal structure and atmospheric dynamics. 81. Some exoplanets have been discovered with atmospheres that show signs of clouds and hazes, similar to those on Earth and other planets in our solar system. For example, the atmosphere of the exoplanet GJ124b is believed to contain thick clouds or hazes that obscure its surface. Studying these atmospheric features can provide insights into the climate and weather patterns of exoplanets. 82. The detection of exoplanets has revealed that some planets can exist in very eccentric orbits, leading to significant variations in their distance from their star and resulting in extreme seasonal changes. For example, the planet HD 80606b has an eccentric orbit that causes it to experience extreme temperature variations over the course of its orbit.
83. Some exoplanets have been found in systems with very active stars, which can have a significant impact on the planet's atmosphere and potential habitability. For example, the planet Proxima Centauri IB orbits a red dwarf star known for its frequent stellar flares. Studying these interactions helps scientists understand the challenges for habitability in such environments. 84. The study of exoplanets has shown that some planets can have rings or ring systems similar to those of Saturn, but on a much larger scale. For example, the planet J1407b is believed to have a ring system much larger than Saturn's, with gaps that may indicate the presence of moons. Understanding these ring systems can provide insights into the dynamics of planetary systems. 85. Some exoplanets have been found in systems where the host star is part of a close binary pair, creating complex gravitational environments. For example, the planet Kepler for 7c orbits within a binary star system, experiencing varying gravitational forces from both stars. Studying these systems helps scientists understand the dynamics of planetary orbits in multi-star environments. 86. The discovery of exoplanets has shown that planetary systems can have very different architectures, with some systems having tightly packed inner planets and wide outer planets. For example, the system around the star HD 219134 has several small, rocky planets close to the star and gas giants farther out. This diversity helps scientists understand the processes that shape planetary systems. 87. Some exoplanets have been found with significant tilt in their orbits known as obliquity, which can affect their climate and weather patterns. For example, the planet Kepler for 13b has an extreme tilt that causes it to wobble, leading to significant seasonal changes. Understanding obliquity helps scientists learn about the factors that influence planetary climates. 88. The study of exoplanets has revealed that some planets can have significant internal heat sources, such as tidal heating from gravitational interactions with their star or other planets. For example, the planet Io in our solar system experiences intense volcanic activity due to tidal heating from Jupiter. Similar processes may occur on exoplanets, affecting their geology and potential habitability. 89. Some exoplanets have been discovered in systems with very low-mass stars, also known as red dwarfs, which are the most common type of star in the galaxy. These planets, such as those in the TRAPPIST-1 system, provide valuable data for understanding the potential for habitability around the most abundant stars. 90. The detection of exoplanets has shown that some planets can have very high surface gravities, much higher than that of Earth. For example, the planet Kepler 10c has a high surface gravity due to its large mass and density. High surface gravities can influence the planet's atmosphere and potential for supporting life. 91. Some exoplanets have been found with unusual orbital configurations, such as retrograde orbits, where the planet orbits in the opposite direction to the rotation of its star. For example, the planet WASP-17b has a retrograde orbit, which challenges existing models of planet formation and migration. 92. The study of exoplanets has revealed that some planets can have very large tidal forces due to their proximity to their star, leading to significant tidal bulges and heating. For example, the planet 55 Concrete experiences intense tidal forces that may cause widespread volcanic activity. Understanding tidal forces helps scientists learn about the geophysical processes on exoplanets 93. Some exoplanets have been discovered in systems with very high levels of radiation, such as those near the centers of galaxies or close to black holes. These extreme environments challenge our understanding of planet formation and survival under intense radiation conditions 94. The detection of exoplanets has shown that some planets can have significant amounts of water, either in their atmospheres or on their surfaces. For example, the planet GJ1-1 is believed to be a water world with a thick atmosphere of water vapor. Understanding water-rich exoplanets helps scientists explore the potential for life and the conditions necessary for habitability. 95. Some exoplanets have been found with very long rotational periods, taking many Earth days to complete a single rotation. For example, the planet Kepler 7-8b has a rotation period of about 8.5 Earth days. Long rotational periods can influence the planet's climate and weather patterns. 96. The study of exoplanets has revealed that some planets can have significant amounts of organic molecules in their atmospheres, which are considered building blocks for life. For example, the planet HD 189,733b has an atmosphere that contains organic molecules like methane. Detecting these molecules helps scientists understand the potential for life on other planets. 97. Some exoplanets have been found with very high orbital inclinations, meaning they orbit at steep angles relative to the plane of their star's equator. For example, the planet Kepler 6-3b has a high orbital inclination, which can affect its climate and seasonal variations. 98. The discovery of exoplanets has shown that planetary systems can have very different orbital resonances, where multiple planets exert regular gravitational influences on each other, leading to stable orbital configurations. For example, the planets in the TRAPPIST-1 system are in a complex resonance that helps maintain the stability of their orbits. 100. The study of exoplanets has revealed that planets can exist in a wide range of environments, from the hot, close-in orbits of hot Jupiters to the cold, distant orbits of ice giants. This incredible range of environments helps scientists understand the adaptability of planetary systems and the various factors that influence their formation and evolution. For example, hot Jupiters like 51 Pegasi b experience extreme temperatures and intense stellar radiation, while ice giants like those in the outer regions of the TRAPPIST-1 system endure frigid conditions. Studying these diverse environments provides a comprehensive view of the potential for life in the universe and the intricate processes that shape the myriad planetary systems we observe. Each discovery contributes to a broader understanding of the cosmos, revealing the extraordinary variety and complexity of planets beyond our solar system. 101. Some exoplanets have been found with highly eccentric orbits that bring them very close to their host stars during part of their orbit, causing them to experience extreme tidal forces and heating. These hot Jupiters, such as HD 80606b, can have temperatures that increase dramatically during their closest approach to the star, leading to intense atmospheric dynamics and potential atmospheric escape. 102. Exoplanets often exhibit variability in their atmospheric compositions depending on factors such as distance from their host star and the planet's formation history. This variability provides valuable insights into the processes governing planetary atmospheres and their evolution over time. 103. The study of exoplanets has revealed that some planetary systems exhibit orbital architectures that are dynamically stable over long periods. This stability can be influenced by resonances and gravitational interactions between planets, such as those observed in the Kepler 60 system. 104. Exoplanets orbiting red dwarf stars, despite their commonality, face challenges such as tidal locking, where one side permanently faces the star. This creates extreme temperature differences between the day and night sides, impacting the planet's climate and potential habitability. 105. The discovery of exoplanets with atmospheres containing water vapor, carbon dioxide, and methane suggests that these gases are common in planetary atmospheres, providing insights into the chemical processes occurring on these distant worlds. 106. Some exoplanets exhibit significant atmospheric escape, where particles from the atmosphere are stripped away into space due to interactions with the stellar wind or intense radiation from the host star. This phenomenon can affect the planet's evolution and habitability over time. 107. Exoplanets found in binary star systems often experience complex gravitational interactions that can lead to variations in their orbits and climates. Studying these systems provides valuable data on the stability of planetary orbits and the effects of multiple stellar companions. 108. The discovery of exoplanets with high levels of irradiation has led scientists to study the potential habitability of planets in extreme environments, such as those orbiting close to their host stars in the habitable zone. 109. Some exoplanets have been detected through gravitational microlensing, a technique that relies on the bending of light from a distant star by the gravity of an intervening planet. This method allows astronomers to detect planets in regions of space that are otherwise difficult to observe. 110. The study of exoplanets has revealed a wide range of orbital eccentricities, with some planets having nearly circular orbits and others having highly elliptical orbits. These eccentricities can influence the planet's climate and seasonal variations. 111. Exoplanets known as mini-Neptunes are intermediate in size between Earth and Neptune, with thick atmospheres primarily composed of hydrogen and helium. These planets are common in exoplanetary systems and provide insights into the diversity of planetary compositions beyond our solar system. 112. The discovery of exoplanets has shown that some planetary systems exhibit orbital resonances, where the orbits of multiple planets are in precise ratios with each other. For example, the TRAPPIST-1 system has planets that are in orbital resonances, which contribute to the stability of their orbits over long periods. 113. Exoplanets with atmospheres rich in hydrogen and helium, such as hot Jupiters, often experience significant atmospheric escape due to their proximity to their host stars. This escape can lead to the loss of lighter gases over time, altering the planet's atmospheric composition. 114. Some exoplanets have been found to exhibit transit timing variations, where the timing of their transits across their host star varies due to gravitational interactions with other planets in the system. These variations provide clues about the presence and properties of additional planets in the system. 115. The study of exoplanets has revealed a population of free-floating or rogue planets that do not orbit any star and instead drift through space alone. These planets may have been ejected from their original star systems or formed independently through gravitational collapse. 116. Exoplanets found in the habitable zone of their host stars are of particular interest as they could potentially support liquid water on their surfaces. Studying these planets, such as those in the habitable zone of TRAPPIST-1, provides insights into the conditions necessary for habitability and the search for extraterrestrial life. 117. The discovery of exoplanets has led to the development of advanced spectroscopic techniques to analyze the composition of planetary atmospheres. These techniques, such as transmission spectroscopy and emission spectroscopy, allow scientists to detect molecules like water, carbon dioxide, and methane in exoplanet atmospheres. 118. Some exoplanets exhibit significant atmospheric dynamics, including jet streams and high-speed winds that can shape their climates and weather patterns. For example, the exoplanet HD 209,458b has been observed with winds reaching speeds of up to 5,000 to 10,000 kilometers per hour. 119. Exoplanets orbiting close to their host stars, known as hot Neptunes or mini-Neptunes, challenge existing models of planet formation due to their proximity to the star and the survival of their thick atmospheres. Understanding these planets provides insights into the processes of planet migration and atmospheric evolution. 120. The study of exoplanets has revealed a population of super-Earths that are larger and more massive than Earth, but smaller than Neptune. These planets, such as Kepler-2b, may have compositions ranging from rocky to water-rich, offering a glimpse into the diversity of planetary types beyond our solar system. 121. Exoplanets with high levels of stellar irradiation, such as hot Jupiters, often exhibit inflated atmospheres and bloated radii due to the intense heat from their host stars. This phenomenon, known as thermal bloating, expands the planet's atmospheres beyond what would be expected based on their mass alone. 122. Some exoplanets have been detected through the technique of radial velocity, which measures the small periodic shifts in a star's velocity caused by the gravitational pull of an orbiting planet. This method has been instrumental in discovering many exoplanets, including hot Jupiters and super-Earths. 123. Exoplanets can have a wide range of surface temperatures, from hundreds of degrees Celsius on hot, close-in planets to temperatures below freezing on colder, more distant planets. Understanding these temperature variations helps scientists assess the potential habitability of exoplanets. 124. The study of exoplanets has revealed that some planets exhibit significant atmospheric hazes or clouds that obscure observations of their surfaces. These hazes, such as those found on GJ1-1b, can affect the planet's climate and the interpretation of spectroscopic data. 125. Exoplanets orbiting red dwarf stars are subject to tidal locking, where one side of the planet always faces the star, the tidally locked side, while the other side experiences perpetual darkness. This phenomenon creates extreme temperature differences between the two sides of the planet. 126. Some exoplanets have been found in systems with multiple stars, known as binary or even trinary star systems. Planetary orbits in these systems can be complex and dynamically challenging due to gravitational interactions between the stars. 127. The discovery of exoplanets has led to the identification of ultra-short period planets, which complete their orbits around their host stars in less than a day. These planets, such as WASP-19b, orbit very close to their stars and experience extreme temperatures. 128. Exoplanets with thick atmospheres composed of hydrogen and helium, similar to Neptune and Uranus in our solar system, are known as hot Neptunes or mini-Neptunes. These planets challenge current theories of planet formation and migration due to their proximity to their host stars. 129. Some exoplanets have been found in systems with eccentric warm Jupiters, which are giant planets with highly elliptical orbits that bring them close to and far from their host stars. Understanding these eccentric orbits provides insights into the dynamical evolution of planetary systems. 130. The study of exoplanets has revealed a population of Chthonian planets, which are the remnants of gas giants that have lost most of their hydrogen and helium atmospheres due to intense stellar radiation. These planets have dense, rocky cores and thin, metallic atmospheres. 131. Exoplanets in systems with multiple planets can exhibit orbital resonances, where the gravitational interactions between planets cause them to orbit in synchronized patterns. These resonances, such as those seen in the Kepler-11 system, contribute to the stability of planetary orbits over long periods. 132. Some exoplanets have been detected through gravitational microlensing, where the gravitational field of a foreground star magnifies the light of a background star, revealing the presence of an orbiting planet. This method is sensitive to planets at large distances from Earth. 133. Exoplanets found in the habitable zone of their host stars are of particular interest as they may have conditions suitable for liquid water to exist on their surfaces. These habitables own planets include Earth-sized planets like Kepler 186f and Proxima Centauri IB 134. The discovery of exoplanets has shown that planetary systems can have diverse architectures, including systems with closely packed planets and systems with widely spaced planets. Each architecture provides clues about the formation and evolution of planetary systems. 135. Exoplanets orbiting close to their host stars, such as hot Jupiters, often exhibit strong atmospheric winds that can reach speeds of thousands of kilometers per hour. These winds redistribute heat and affect the planet's atmospheric dynamics. 136. Some exoplanets have been found in systems where the host star is a white dwarf, the remnant of a star that has exhausted its nuclear fuel. Planets orbiting white dwarfs, such as WD-1856b, challenge theories of planet formation and evolution in post-main sequence stars. 137. Exoplanets with orbits that are tilted relative to their host star's equator can experience significant seasonal variations in temperature and sunlight. Understanding these orbital inclinations provides insights into the climate dynamics of exoplanets. 138. The study of exoplanets has revealed a population of inflated super-Earths, which are rocky planets with radii larger than expected based on their mass. These planets may have thick atmospheres or volatile-rich compositions that contribute to their inflated sizes. 139. Some exoplanets have been detected through the transit method, where the planet passes in front of its host star, causing a slight dimming of the star's light as seen from Earth. This method is sensitive to planets that are aligned with our line of sight. 140. Exoplanets found in systems with multiple stars, such as circumbinary planets, experience complex gravitational interactions that can affect their orbits and stability. Studying these systems provides insights into the dynamics of planetary formation in multi-star systems. 141. The discovery of exoplanets has led to the identification of eccentric hot Neptunes, which are Neptune-like planets with highly elliptical orbits that bring them close to and far from their host stars. These eccentric orbits challenge theories of planet formation and migration. 142. Exoplanets in systems with multiple planets can exhibit transit timing variations, where the timing of their transits across their host star varies due to gravitational interactions with other planets. These variations provide clues about the presence and properties of additional planets in the system. 143. Some exoplanets have been found in systems with circumbinary planets, which orbit to stars in a binary star system. These planets experience complex gravitational forces and orbital dynamics due to their dual stellar companions. 144. Exoplanets with thick atmospheres, such as hot Jupiters, often exhibit significant temperature variations between their day and night sides. This phenomenon, known as day-night temperature contrast, influences the planet's atmospheric circulation and weather patterns. 145. The study of exoplanets has revealed a population of disintegrating planets where the intense radiation from their host stars causes their atmospheres to evaporate and escape into space. These planets may leave behind a comet-like tail of escaping gas. 146. Exoplanets found in the habitable zone of their host stars may have conditions suitable for liquid water to exist on their surfaces, depending on factors such as atmospheric composition and greenhouse effects. Understanding these conditions helps assess the potential habitability of exoplanets. 147. The discovery of exoplanets has shown that some planetary systems exhibit compact systems where multiple planets orbit very close to their host star. These systems challenge theories of planet formation and stability in compact environments. 148. Exoplanets can have a wide range of orbital periods, from just a few hours for ultra-short period planets to thousands of years for more distant planets. Each orbital period provides insights into the planet's distance from its host star and its dynamical environment. 149. Some exoplanets have been detected through direct imaging, where astronomers capture images of the planets themselves rather than detecting their presence indirectly through their effects on their host stars. Direct imaging is challenging but provides valuable data on the physical properties and atmospheres of exoplanets. 150 exoplanets orbiting red dwarf stars, despite their commonality, face challenges such as intense stellar flares and radiation that can affect their atmospheres and potential habitability. Studying these planets provides insights into the conditions necessary for life in orbit around low-mass stars. The exploration of exoplanets has revolutionized our understanding of planetary systems beyond our solar system. From the discovery of hot Jupiters orbiting close to their stars to the detection of Earth-sized planets in the habitable zones of distant stars, each new finding expands our knowledge of planetary diversity and formation mechanisms. The study of exoplanets continues to unveil surprises, from bizarre atmospheres rich in hydrogen and helium to the intricate dynamics of multi-planet systems. These discoveries not only challenge existing theories, but also offer tantalizing prospects for finding potentially habitable worlds and understanding the conditions necessary for life elsewhere in the universe. As technology advances and observational techniques improve, the future promises even more remarkable discoveries in the field of exoplanet research. Each new exoplanet adds a piece to the puzzle of planetary evolution and provides valuable insights into the vast cosmic tapestry of planetary systems. Good night. Sleep well. If you have more questions or need assistance in the future, don't hesitate to reach out. Take care